All right, so we're recording. Hi, everyone. Welcome to the Protocol Labs Research Seminar Series. Thank you. Special welcome to those of you watching the recording. Just a reminder that if you want to be informed of future seminars or stay up to speed on what we're doing at Protocol Research, you can visit research.protocol.ai, drop your email in the footer, sign up for announcements, quarterly newsletters, etc. You can also find a playlist of previous seminars on the outreach page of our website under public talks. And you can also find other ways to connect to what we're doing there, link to current research funding opportunities through our RFP program, among the things that you'll find. Ariel has said to go ahead and interrupt him as much as you want or need to along the way with questions. So I will let you do that. Just a reminder that I might jump in if we get stuck on a line of questioning and it seems to be taking us off course, just to moderate. But other than that, please feel free to jump in with your questions. Our speaker today is Ariel Gabizon. Ariel has a PhD in computer science from Weizmann Institute and was formerly a researcher and an engineer at Zcash, as well as here with us at Protocol Labs. He's now chief scientist at AZTEC, working on making ZK Snarks more efficient. His talk today is on polynomial protocols, as you can see. And Ariel, I'll let you take it from here.
Thanks. And yeah, about the interruption. So yeah, please feel free to interrupt by speaking, because sometimes with Zoom, it's a process to dig where the written question is. Right. So yeah. So this is sort of polynomial protocols is sort of an abstraction I came up with that kind of to allow, for one, allow questions about ZK Snarks to sort of be worked on by people like, say, not interested or not familiar with cryptography. So, and I'll say soon what I mean by that. Yeah, so again, these slides sort of assume, I think, some background in ZK Snark. So please interrupt also, like with the question, what is a ZK Snark, and so forth. Yep. Right, so kind of, so what's been going on with Snarks lately? So I guess, yeah, I guess I'll say what the acronym means. It means succinct non-interactive argument of knowledge, or ZK Snarks, zero knowledge, succinct non-interactive argument of knowledge. And the idea is to give a short proof of some secret information. So for example, you have your encrypted balance account. You want to prove that you give a short proof that you have at least $10,000, and you want that proof not to give any additional information. So I won't know if you have $10,001 or $5 million, but I will be convinced from the proof that you have at least 10,000. And sort of what's been going on in the space in the last few years. So what an approach, it's funny that I call it traditional approach because we're talking about things that are like 4 or 5 years old. The approach that, you know, led to Zcash, for example, of how to construct these proofs is you start with some program, think of it as a C program that describes the computer program you want to prove statements about. And then you translate to this program to some set of constraints. And what's been really popular in the last few years is what's called R1CS constraints, which are sort of degree 2 equations. So you have some C++ program like describing a hash function, and you translate it to like degree 2 equations over some field that are sort of equivalent to this program. And basically that is the sort of the Snark programmer that's pretty much all you do. That's where your job sort of ends. And then this thing is fed into this more algebraic machine that compiles these constraints to polynomials in some way, and somehow these polynomials allow you to construct these Snark proofs. So what we're seeing, like really recently, like in the last year, I guess, is that it can be more efficient, much more efficient sometimes, to sort of directly play with the polynomials. So sort of directly translate, when you're doing this translation process of your C program to something the Snark machine can eat, to sort of try to directly work with the polynomials to get the, and we've been seeing really recently that this can give a really good efficiency boost. And this, I'm sure it sounds a little vague. I hope it'll be a little more concrete soon. Yeah, and for example, if you look at this reference, this footnote below, this is an attempt of Vitalik and others in the Ethereum Foundation to sort of solve scalability problems with this approach. Okay, so this brings us to this abstraction that I really like, called polynomial protocols. So this will be a sort of abstract definition, but then I'll say why it's sort of I'll motivate it. So in these abstract protocols, so we have a prover and a verifier, like we have many times in these crypto protocols. We have like a prover and verifier, and sort of all the protocol is, the communication is in polynomials. So we have like a pre-processing stage where the verifier chooses some polynomials they like, and then the prover the prover communicates with the verifier. But here we're thinking of the prover's messages, we're thinking of them as going to some ideal party, and the messages must be polynomials of degree smaller than some fixed integer d that we agreed on. So if the prover tries to send something else, then everything is like aborted. So this is like how the protocol goes. The prover sends polynomials, the verifier, you can think of him as just sending like random coins. And then, okay, what happens at the end of the protocol? The prover needs to decide if to accept or reject. So how does the verifier decide this? He chooses some polynomial identity and asks the ideal party, does this identity hold between the pre-processed polynomials that I chose and the polynomials the prover sent, and accepts if and only if this is the case. Okay, and now we're going to define some complexity measure of this protocol, which is just basically the sum of all the polynomials the prover sent. And sorry, ignore the first line with this capital D. That's sort of a typo. So we're defining this sort of measure of the protocol, which is the sum of degrees of polynomials the prover sent. And now, okay, this like it seems pretty abstract. Like, why am I talking about protocols where polynomials are sent and the verifier can check some identity between them. So the sort of the point is using this magical thing that has become very important in the last few years called the polynomial commitment scheme. We can compile such an abstract protocol into a real one where each message of the prover that was like a whole polynomial becomes just 32 to 48 bytes. And then the sort of the prover cost of this protocol is going to be basically the sum of the degrees. And basically the way this works is like by opening all the polynomials at a random point and then checking this identity at a random point. So yeah, so any questions so far? Okay, and so if you look at like what's going on in a lot of the sort of proving systems, you see that like this is related, but it's not the exact abstraction that corresponds to most protocols, and you need a little tweak to capture that, and this is what we call ranged polynomial protocols. So in these protocols, we have an additional parameter, which is like this fixed special subset of the field, and so things, the protocol works the same way. The prover sends polynomials. The verifier asks if some identity holds between these polynomials. But instead of asking if they hold like as an identity, the verifier asks if they hold just on the points of this set H. And it's easy to go from one to the other, because suppose you wanted, like with a polynomial protocol, to check if some identities hold on a set H, then you could just run the so you could just run like the H-range protocol. You could just simulate it by running it as usual, just running it. And then you reach the point where the verifier wants to ask, well, do these identities hold on H? And then you're only allowed to ask if some identity holds on, identically. So the way you can do that is after P is finished sending all the polynomials, V chooses some random coefficients, and P sends some polynomial, and now V checks this identity. This random combination of the identities, does it equal T times ZH, where ZH is the polynomial that's 0 on H. And the point is that, like, something is since ZH is exactly the polynomial that's 0 on H, then this identity will hold if and only if, like, it will hold for some polynomial T if and only if the left-hand side is 0 on T. And the left-hand side will be 0 on T with high probability if and only if both P1 and P2 are 0 on H, right? Because these are random coefficients we chose after P1 and P2 were fixed. And this sort of motivates defining the complexity of an H-range protocol the same as before, but with this additional D minus H factor, where D is the max degree of an identity being checked, right? Because this D minus H will be a bound on the degree of this T that the prover needs to send. Okay, so I mean, that maybe was a little abstract for someone who's never seen something in this sort of context. But let's try to give a somewhat more concrete example. So suppose we have two vectors. We're given two vectors of values, and to connect it a little to before, you can think of it as, so how is like the verifier given these vectors, right? So always in these Snark contexts, we don't want to give the verifier long things. We want our proofs to be small. So the verifier is going to be given some what's called polynomial commitment to these two vectors. And suppose you want to check that these vectors are equal as multisets, meaning that like they're right. So B1, so it's the same values, but just maybe under different order. So how can you sort of concisely check whether like these are the same set, the B's and the A's? So that the first thing you might try is just, well, let's take the product of the B's and the product of the A's. But the products could be the same. Could be the same even though the B's and A's are different, right? Like suppose the A's are 1, 1, 1, and the B's are like half 1, 2. So right, the products will be the same even though they're different sets. But what's easy to see with what's called the Schwartz-Zippel lemma is that if you take like a randomized product, right, you shift everything by some random gamma, then with very high probability, the A's and the products will be different if the A's and B's are different vectors or different sets. Right. Right. Okay. So to translate this more to our language, we can think of it as, okay, we're F and G are polynomials, and we want to check if their values on this set H are the same, but maybe in different order. So for this, we're going to need a tiny mathematical interlude. So it's going to be really useful to work with what's called multiplicative subgroups. So this is going to be like some subset of our field where that are all powers of the same element alpha. And some notation that will be useful for us is what's called using like a Lagrange basis of the set H. So right, so this is going to be just a set of polynomials that the ith polynomial is going to be 1 on alpha to the I and 0 on alpha to the j for other j's. So this is like what's called the Lagrange basis for H. And a really useful property is that when H is like just this sequence of powers, a multiplicative subgroup, these LIs, although like their degree is going to be like n or n minus 1, but there's going to be a verifier can compute them himself in like logarithmic in n time. They have a very sparse representation. Right. So basically, using this idea of doing randomized sort of checking a product of like a random shift of everything. So this multi-set check, it reduces to given two polynomials, wanting to check if the product of values of these polynomials is on the set H is the same. Okay, and so this paper that we wrote about a year ago, Planck, its core contribution was sort of a really efficient protocol for this problem. So how do you check that the value of the product of values of two polynomials is over some subset H is the same. So So what you do is the proofer will construct some other polynomial z that aggregates these products. So the like partial product. So z will sort of start at 1, and then z at the I point will aggregate the ratio of the products on the first I minus 1 points. And now, okay, so the prover sends this polynomial, and now what identities does V check? So V wants to check that really Z starts at 1. So how do you check that? So remember, we have to phrase our checks as checks on all of H. So this is why we check, does L1 times Z of X minus 1 equal 0? So this is exactly equivalent to checking if Z of alpha is 0, right? Because we're checking this thing on all of H. So on all points except alpha, L1 is 0. So the product will be 0. Except on alpha, where L1 of alpha will be 1. So the 3-point point will be equivalent to checking that Z of alpha is equal to 1. And the second check, it checks that really Z. So right, we want to check that Z starts from 1, and that Z is really accumulating the values of f over g. And this is what 3.2 does, right? It checks that Z on the next point, Z at alpha x, is equal to the Z on the current point times f over g. So you see here a very concise thing. Similar protocols for the same thing were more cumbersome, and one advantage we have here is because we're working with this multiplicative subgroup, expressing this thing of the next point is simply multiplication by alpha, right? Because alpha to the I plus 1 is the next. And so right, so I claim to you that these checks sort of are, because right, we're checking these identities on all of H. So we know that Z starts from 1. Z is accumulating the values of f over g. And we also know in a sense that Z, right, because the group wraps, like alpha to the n is 1. We know sort of that Z, like Z of alpha to the n is going to be equal. We know that like Z of alpha, we know that it's 1, but we also know that it's equal to the product of f over g from 1 to n. So this means that the product of f over g is 1, which exactly means that the product of f and the product of g are the same. Right. So and now the question is, what's the complexity of this thing? According to this measure we defined. Well, so the prover, right? The prover is sending this polynomial z, which has degree n, and is checking the identities that the verifier is checking. Their maximal degree is going to be 2n, right? Because we have this z times f. So n plus 2n minus h, it gives us 2n. Right. Okay, so now we sort of come to the kind of my motivation for giving this talk is sort of to present this open question. So I don't think this product check or this multi-set check, I don't think it can really be improved. It seems to me pretty optimal. But somewhere where I'd be glad for people to look into and try to improve is this problem of range checks. So this is a problem that's extremely important in ZK snark constructions, and you can think of it as like you have some fixed integer m, you have some polynomial f, and you want to check that all of f's values on the set H are in the range 1 to m. So really a lot of anybody who's spent time constructing snarks has probably experienced that a lot of the sort of prover complexity ends up being related to these range checks. So really to sort of how I want to wrap up this this talk, I want to show you our or a slightly simplified version of our range check, and like I said, really my motivation is to see if someone can improve this. So yeah, so to present it here, I'll make this simplifying assumption that really f contains the values 1 to m. So of course that's not necessarily the case. You know, maybe f just contains some of them, but let's make this assumption, sort of to just, you know, give the main idea of the protocol. The main thing we want to check is that f doesn't contain values outside this range. So how the protocol will work is that the prover will compute a sorted version of f. And what I mean by this is another polynomial s of the same degree that has the same values as f, but they're ordered. So right, s of alpha to the I will be smaller than s of alpha to the I plus 1. So just a polynomial that has the same values as f, but sorted. And prover will send s. And right now, what will the verifier do? So the verifier will do this multi-set equality check between s and f. So after doing that, it's enough for, right, we know that s and f have the same values, and now it's enough to check that, it's going to be enough to check that s has values only in this range. Now also the verifier will check that s begins at 1, s ends at m, and for each other x in the range, the prover will check this identity that s of and right, really what this identity says is simply that if you look at like one value of s compared to the next value, then like it changes by either 0 or 1, right? This thing like, does the difference between the next value squared and the current value squared equal the difference not squared? So right, this will only be satisfied by 1 and 0. Right, so what do we know? We know that s, it starts at 1, it ends at m, and it only changes by each time by 0 or 1. So right, it can never go outside this range 1 to the m, right? Because it's not doing any jumps. It's, you know, if I know you start at 1, you finish at m, and you're each step you're just either not moving or either going up by 1. I know you're not doing some crazy things like, you know, go up to 5m and go back down to 2m and to m and so forth. So the complexity of this protocol will end up being 3n, and it's sort of dominated by these two. Yeah, but well, just from the contribution from the multi-set check and this check in step 3.4. But anyway, and sort of I assumed so that I could really start at 1 and end at m and take these small steps of I needed to assume that, right, I can only do that if really f contained all the values. Otherwise, maybe sometimes I would need bigger jumps. So to solve that problem, you need to put into f the like sort of dummy values from 1 to m. But that's not a big deal. And the main, but I think the main interesting question is, can you get a protocol with the same or almost the same complexity that can work for a larger range, like 1 to m squared? Yeah, so I think that is it. Yep.
Did you want to open it up to questions?
Yeah, absolutely.
Okay. And then my usual caveat that if you don't feel like being on the recording, you can just type your question into the chat box and I'll read it for you. Nothing from Irene or Nicola? All right, I'm going to recording and see if anyone has any thoughts to share after we are off. Thank you, Ariel, for this. Super appreciate you taking the time to give this talk, and it's great to have you back in the PL space.
Yeah, thanks a lot for inviting me.